Good day to everyone. I am Charina Gracia B.Banaay from the Institute of Biological Sciences, UPLB. I am here to present our paper entitled Promoting Sustainability, Resilience, and Environmental Rehabilitation in Copper-Contaminated Lowland Rice Fields in Mogpog, Marinduque using Trichoderma technologies. My co-author is Dr. Virginia C. Cuevas. This presentation reports an INREM theme relevant information gathered from our recently concluded project funded by DABAR. The objective of this presentation is to provide information on how trichoderma can help support sustainability goals, increase resilience in crops and communities, and help rehabilitate heavy metal contaminated agricultural soils. The picture shows an area in Barangay Ino in Mogpog with the mined out area adjacent to a rice field with moderate levels of soil copper contamination of around 150 ppm. The Mogpog story is a tale of two disasters related to mining accidents that affected several towns in Marinduque, especially Mogpog. The first disaster occurred in 1993 when a mine tailings dam collapsed and spilled contaminated water onto the surrounding land. The second one happened in 1996 when a drainage tunnel of a mine tailings pit burst and inundated the Mogpog River and surrounding lands with heavy metal contaminated water. The result is a phenomenon we call acid mine drainage and also caused declines in crop yields for agricultural areas. A few studies were conducted in the early 2000s and 2010s to look into the effects of these two mining disasters on the community and the environment. In the early 2010s, a study on reforestation of mined out areas, mainly in Barangay Kapayang, was conducted by several UPLB researchers. However, the rehabilitation of affected agricultural lands was not addressed. So in 2017, we started a project entitled Use of Agri-Waste Compost and Trichoderma Microbial Inoculant for LGU and community-based rehabilitation of agricultural lands damaged by mine wastes in Mogpog, Marinduque. This project was funded by DABAR and ended last July 2021. After the two mining disasters, the Mogpog story continued as a series of unfortunate events. Heavy metal toxicity reduced the yield of crops and resulted to several health concerns as mentioned by residents during an initial survey that we did. Reduced crop yield means reduced income, so they have fewer resources to buy inputs and support farm operations, as well as family needs. In addition, various abiotic and biotic factors put more pressure on the situation. This has led to increased poverty in the area. A 2008 survey of Mogpog showed that 50% are income poor and 30% are experiencing food poverty. In our survey conducted at the start of the project in 2017, poverty has grown to 67%. More than half of the households have 4 to 6 members, and almost half are relying on single farmer incomes. The situation in Mogpog has worsened through the years, precipitated by the mining disasters that happened more than 25 years ago. Science-based interventions are needed to help the community overcome the effects of heavy metal contamination. Hence our project. Here's what we did. We first coordinated with the Mogpog LGU through the mayor, the municipal agricultural officer, and the municipal environment and natural resource officer. We solicited their cooperation and also help in hiring science aides from among the local residents to help us coordinate with the farmers. Then we conducted several seminars and training workshops involving more than 200 farmers from various barangays. We did an initial survey to get baseline information on the farmers and the areas of study. Then we did several field experiments covering 4 cropping seasons and involving nearly 200 rice and vegetable growers, covering about 100 hectares of agricultural lands. Our cooperators were taught how to apply 2 trichoderma-based technologies to their crops and compare the outcomes with control plots. Finally, we did exit surveys, wrote the terminal report, and submitted articles for publication. So here's our Mogpog story. Many areas are severely copper contaminated with more than 200 ppm of soil copper. Of the 43 soil samples collected from 16 barangays, 28% have normal soil copper levels of less than 50 ppm, 9% have low soil copper contamination of 50 to 100 ppm. 23% are moderately copper contaminated with 101 to 200 ppm, and 40% have severe copper contamination levels of more than 200 ppm. In the whole duration of our study, we observed severe copper contamination levels of up to 1,300 ppm. Severe contamination was also observed from samples taken 1 meter below the soil surface. It is highly possible that the contamination reaches much deeper into the soil profile. Due to the soil contamination, crop yields dwindled. Farmers reported a 50% reduction in rice yields. Our field experiments showed a reduction of 21 to 66% compared to the control plots, and a 72% reduction compared to the potential yield. The farmers also reported reduced harvests from other crops, such as vegetables, root crops, and fruits. This has led to increased poverty due to reduced income from harvests. There were also problems with various biotic and abiotic factors such as pests, diseases, and the El Nino. The farmers have a reduced capacity to cope with these problems because of poverty. It's a vicious cycle where poverty leads to more poverty. So how are trichoderma technologies able to help resolve the Mogpog situation as shown here? Our results show that trichoderma is able to increase the yield of rice and other crops by 12 to 200%. It's amazing. It seems unbelievable, but this is not an uncommon outcome. Many previous studies have shown that huge crop responses to trichoderma application are observed because of the systemic effects of the fungus on plant metabolism that act synergistically, leading to plant growth promotion. A partial economic survey at the end of the project also shows that there is more than 20,000 pesos increase in income per season, which is attributable to the combined increase in yield and savings from reduced inputs and losses due to pests and diseases. The overall effect of trichoderma is increased resilience to various environmental stressors. Let's go back now to sustainability, resilience, and environmental rehabilitation. How does our project help achieve, first, the UN SDGs? Trichoderma supports SDG numbers 1, 2, and 8 through plant growth promotion and increased resistance, leading to improved crop productivity, resulting to greater harvests and higher income. Higher income means alleviation of poverty, enough resource to feed the family, and economic growth to support all other needs. Trichoderma also supports SDG numbers 11 and 12 because it is based on ecologically sound principles that contribute to the following. Number one is waste management through composting of crop residues and other municipal wastes. Second is resource efficiency through reduction of fertilizers and pesticides. Third is adaptation to climate change through induced resistance to abiotic stressors such as drought. And finally, sustainable crop production systems through plant growth promotion with less organic fertilizers and pesticides, and promoting soil health through addition of organic matter and enhancement of beneficial microbial interactions, thus reducing the damaging effects of agriculture on the environment. In addition, Trichoderma supports SDGs 13 and 15. It helps in strengthening the resilience and adaptive capacity of farmers to climate-related hazards such as drought. Trichoderma technologies also promote soil health by capitalizing on beneficial microbial interactions and activities. It also helps in the rehabilitation of degraded soils damaged by pollutants. Finally, our whole project supports SDG 17, as it relied on healthy partnerships between the university, LGU, farming community, and business sector to achieve the goals of the project. We can say from all the benefits we observed that Trichoderma is a toolkit for resilience. It serves many functions, such as biocontrol, biofertilizer, compost activator, bioremediation agent, plant growth promoter, and inducer of systemic resistance in plants against pests, diseases, and detrimental abiotic factors. All in all, this increases the resilience of plants and communities to various stressors. Trichoderma is an effective agent of soil rehabilitation. It functions for mycoremediation, enhancement of beneficial plant-soil microbe interactions, agent of decomposition and nutrient cycling, and it helps alleviate soil sickness through biocontrol and promotion of soil health. The end result is the rehabilitation of degraded soils. In conclusion, our project shows that trichoderma-based technologies help promote the achievement of sustainable development goals, increase resilience of crops and communities to various biotic and abiotic stressors, and help rehabilitate degraded and damaged soils. Finally, this is a picture of some of our farmer cooperators during one of our training workshops. Thank you all for listening.